Subscribe now and click on the bell icon to never miss learning from Vedantu.
So in today's class, we are going to link a few things. So let's talk about the agenda today. So we are talking about the magnetic intensity. That's the external field that is trying to create the magnetic behavior in a material. Then we will talk about the magnetization that is induced in the material, and then we'll talk about the permeability, and then we finally will talk about the susceptibility. So these are the four things that we are trying to cover today. But believe me or not, if you've already studied it, good. But many students find it confusing because there are so many new terms introduced in today's class. So you have to pay extra attention that what you were doing so far. So let's get started with tiny little question here, something humorous, something out of the box, please. Something different. So what do you think? Yeah, so yeah, that's the answer. I was also thinking, Trisha. Somebody who has something different than that. Ashik. Okay, Ninad says teddy bear. Arvind gave a different answer here. Okay, so I was actually Ashik, Trisha, me were actually thinking bear without ear is okay. So Atri says anything it can't hear. Yeah, that's the good one. Atri says you can say it anything, but because it can't hear anyways, right? Freddy, not Teddy. Okay. Heady, Ocha. Heady, not Teddy. That's what Ninard says. Okay. Teddy B, Abhinya says, and most of the others, rhythm and all, everybody has said B, right? Yeah, that's what I was also thinking. Arvind Thakur said BEE as in B, right? It's called a bee, as in bumblebee, right? Humming bee. Okay, so just to lighten up the mood here. So now let's get serious here. Today we are going to start with the Curies law. What is Curies law? Magnetization. Remember what is magnetization? Uh, so let's study. There is a magnetic field here. There is some magnetic field here. Right? Now, when you put in a material here, let's talk of iron. This gets magnetized. So there is a magnetization induced in it. Right? So I'm going to repeat what I said. There is an external magnetic field because of some north pole here maybe, or because of some south pole here, or because of combination of north and south pole. Now, because of the combination there was some magnetic field here already present. I put a piece of metal here, maybe iron, cobalt, nickel, or something else also. It is going to be magnetized. Okay. Now, this magnetization depends on few things. So first of all, it depends on how strong the magnetic field here is. Right, stronger the magnetic field, the stronger the magnetization will be. But then it also depends on the temperature, as in inversely to the temperature. So if you increase the temperature here, there is more of randomization that happens here, and that is not going to let the domains align. Think about that way. Because of randomization, alignment is missing now, and that is why as you increase the temperature, magnetization reduces. And you combine these things by one constant that's called the Curie constant, B by T. Anybody who did not understand this simple concept here, magnetization is equal to a constant times magnetic field over the temperature. Okay, seems you have understood that, Lakshmi. Anybody who did not understand? So Nina seems to have understood. So this is what we are talking about. Right, as you increase the temperature, that magnetization reduces. C is the Curie constant. And then we can also go back and say, remember, magnetic field is actually mu naught times the intensity there. So you can instead of this, you can also say C times mu naught H over T. No, that constant will depend on material, right? So there's no one value in Ninard. That's a material property, right? Okay. So now let's study relation between these few terms that some students find confusing. I think this all we have covered, and I'm going to recap all this on one page. I think I will recap all this on one page. Instead of going through these slides, let's actually cover everything. So there is something called magnetic field intensity, right? How strong is the, so remember, for a solenoid, we did this yesterday only. Magnetic field is equal to mu naught times Ni. This thing is H. It's the strength, right? And then depending on if it is air, it's mu naught times of that, or otherwise it's some material, then it is times of that. So very first thing that you will learn is B is equal to mu naught H. This expression, please remember this. The other thing that we studied was the magnetization, right? Magnetization is because of the presence of this, how much is the magnetization that happens in a given material in the field of B. Okay. Now the new thing that we learned today is the magnetization actually is equal to constant, Curie constant, multiplied by this field over the temperature, or you can also write it as this much, right? Anything that is not clear so far, and I think we pretty much covered it. But then there's another thing that we studied yesterday was susceptibility. Remember, susceptibility is how much of magnetization is induced because of a given magnetic field, right? So you can also plug in, instead of B, M by Xi. Good evening, Abhiraj. So these are few things that we studied yesterday, and we are trying to revise those as of now. If there is no doubts, we are going to the question answer session after that, like question session. Is everything clear? Oh, clear. Okay. So let's start this. So magnetization is equal to CB by T, right? So you bring B here, and then you say, okay, magnetization by B is equal to C by T, right? But this itself is Xi. That's what you're talking about, the Xi. Now C is obviously a constant, so susceptibility is inversely proportional to temperature. So then you can write it as this by this is equal to temperature 1 over temperature 2. So temperature 2 is temperature 1 300 times the first susceptibility divided by 1.8 times 10 to the power minus 5, and that gives you 200 Kelvin. That's your answer. Let me know if any part has to be revisited. Yeah, Grishma Reddy is also from Hyderabad. Okay, let me move on to the next question then. Yeah, anybody who could do this, please? It's the same kind of question that we did just now. Yeah, I will actually give you more time. That's fine. Thank you for answering. Like, many students have given the answer so far. I can't even take the name. So many students. Thank you. Rhythm, Lakshmi, Aryan, Trisha, Rukaya, Atri, Sai Kumar, Monisha, Aryan, Malik. Thank you, everybody. Right? Same thing as before. So susceptibility 2 by susceptibility 1 is equal to temperature 1. So T1 by T2. That's all. So I'll just show you the screen. You can take a screenshot of this. Same thing. You just have to plug in the values. Yeah, Abhinya, thank you for that. So let's go to toroid, but before that, has everybody understood? Yeah, thank you, Aryan Malikia. Because there is a magnetic field here. This is a magnetic field, right? This magnetic field is going to magnetize the iron, right? So let me write that with red color. So the magnetization that will happen inside is going to be equal to susceptibility, and I think there is another slide for this, because this you will find actually little confusing, but I'll still do that. Right. So there is some magnetization that happen, and I'm going to link it to susceptibility later. But that magnetization itself will create another magnetic field. So I'll repeat what I said. So you have a toroid. Toroid has a current going through that. That current will induce a magnetic field inside. That magnetic field will magnetize the iron core. But now, since iron core is also magnetized, it will create its own magnetic field, right? Due to magnetization. So the magnetization will create its own magnetic field. And the total magnetic field, and let's call this naught, is going to be the sum of these two. Right. But then what is M? M actually is basically, M also depends on what is, so remember, magnetization per unit magnetic field was susceptibility, right? So we will do this at a later point of time. Anything that is not clear so far, I don't want to jump ahead right now. We'll talk about susceptibility later. So what we are saying is, this is the contribution from the current flowing in, and this is the contribution from the iron core. Is that clear to you? Everybody is clear? Okay. Uh, so let's go further on these discussions, and this is what I was trying to tell you. Right. Yeah. So, what is it? Why aren't we? What is it? I'm not getting, Abhiraj. What are you trying to say? Abhiraj, can you type your statement again? So anybody who did not understand what I wrote here. Okay, so let's actually take another step here and complete this. So remember this. I'll write it as a side step here. Susceptibility is the amount of magnetization induced per unit intensity there, right? So you take this further, and then you can write it as this H plus mu naught times susceptibility of H. So mu naught H 1 plus xi. Right. So just now, by introducing this core, I have this extra piece in here, right? And this is actually what is called mu r. So I'll write it with a different color. This thing is called mu r. So overall, what you have is mu naught mu r times of h. So this is something new now you learned. So relative permeability actually itself is 1 plus susceptibility. No, so okay, that's what Abhiraj you were asking. I mean, I didn't understand your statement. Why aren't we taking mu r? So yeah, we have taken mu r now, right? So we are trying to say, okay, this is actually mu r. Right? So contribution from the current, contribution from the iron core. That iron core actually is mu r. When you're plugging in mu r, actually, when there is a core inside, that's what you do, right? So when you have a solenoid here, you say magnetic field is equal to mu naught Ni, but then as soon as you plug in some core here, you say, oh, I'm going to multiply this by mu r, right? So that mu r itself is 1 plus xi. Uh, so let's go through this. Anybody who does not understand some part of this slide, let me know immediately. Is anybody not clear with some part of this? Or if it is completely confusing, I will do it one more time for next 5 to 10 minutes. Okay, then in that case, I will move on. Okay. So somebody did not understand 1 plus xi thing. Okay, so somebody is saying, what's the reason we do all this? We are trying to see how much of magnetization is induced in there, right? I think I will explain one more time everything. So let's say there is a solenoid. We'll start the study with a solenoid. Okay, this solenoid has a magnetic field inside of it. So inside there is a magnetic field that is induced, and that is equal to mu naught Ni. Is this clear to everybody? Is this clear? If it is not clear, just write no. Okay, don't write yes. If it is not clear, write no. Okay. So this is the magnetic field induced inside of it, and this quantity we are calling it as H. This is the quantity that is called H. This is the magnetic intensity. I will keep writing that also, whatever I speak. This is the magnetic intensity. So then what we are saying is magnetic field induced is equal to mu naught times of magnetic intensity. Okay, we'll take a second step here. So second step would be you have the solenoid, and then you take a piece of some material in here and you place it inside of it. Okay. Now how much is the magnetic field? Now B is equal to mu naught mu r Ni, right? Right. So everybody knows this. You have done this in grade 10th also. If you have, I'm not sure. If you did a little extra than what you were supposed to, you would have done that. But that's fine. So this is the contribution from the iron core. Does everybody understand this? So this is the contribution. So I'll write it with blue color because this iron core is blue. This is contributing as R, right? So mu naught was for vacuum if there was vacuum or air inside. But as soon as you put the soft iron, remember you studied in grade 10th, how do you increase the strength of a solenoid? Number one was increase the current. And you can see why. Because if you increase the current, magnetic field goes up. It's clear now. Second was like increase the number of loops per unit length, and that's obvious. B is directly proportional to N. Number three, you studied introduce a soft iron core. Now this is what soft iron core is doing. It's actually increasing the magnetic field by that number now, right? Clear so far? Clear? Now let's see, take it from a different perspective. I'm not reading the chat box now, except if you don't understand, you just write no. Okay. Now, looking at all this story from a different perspective is what we are doing now. So we are saying, okay, let's say there was a solenoid in here. Good, great, good job. So that solenoid actually had H inside of it, right? So there was a magnetic field inside of it. Now we are saying when we keep iron core inside that, what happens to that iron core? This iron core gets magnetized. So this blue color gets magnetized. Okay. Now, how much does it get magnetized per unit of intensity? There is called Xi. So it has got magnetized. So that magnetization itself creates a new magnetic field because there was a field of the current. Now, if this has become a magnet, it will create its own field. And that field, let's call field because of magnetization, is mu naught times of M. But that you can also write it as mu naught times of H times Xi because of above expression. So now you say B total inside is what you had earlier, which was mu times H, right? That's the contribution from the wire plus mu naught times H Xi. But then you can take this out, mu naught H, and then say 1 plus Xi. Now, if you compare these two equations, which I will encircle here, don't you think 1 plus Xi itself is mu R? Right, that is mu R that we are talking about. Mu R is actually 1 plus the susceptibility. Now, please, I will be quiet for 2 minutes. Try to understand all this from again yourself, and ask me questions. This is all that we are learning today. We are doing question based on this one slide only. So I can explain again. I'll be quiet now. Sorry. Yeah, Arvind Thakur, thanks for asking that question. Arvind is saying, can other substances be used in place of iron? You will get this answer in the next session, actually. Okay, when we study retentivity and all that, you will get it. You can use steel, but steel would be a poor choice. I will answer that briefly after this slide, but so more than 23 students are in the class right now. Anybody has any question? Anybody who's new here for the first time? I mean, I doubt that, but anybody who is here for the first time? Okay. So we will move on. Nobody is asking any questions. I will just answer one of the question that Arvind Thakur asked, why only soft iron? I will answer from qualitative point of view, not quantitatively, right? Quantitatively, we will see in the next class. Oh, did I do that? Sai Kumar, thank you for pointing out mistakes. Like Sai Kumar has pointed out mistakes. Sorry, Sai Kumar, if I said that. So this is this. And Sai is saying, by mistake, I wrote somewhere M by B. I take it back, Sai. I'm really sorry if I did that. Okay. Thank you for pointing that out. So it means you're paying attention. Yeah. So now we have a few choices, right? We can, what about steel? Steel is ferromagnetic. You can make magnets out of it. And then you can use soft iron. You can make magnets out of it. So which one do you choose? The answer will be in the properties here. Steel is difficult to magnetize and difficult to demagnetize. So it's difficult to magnetize, but then once it is a magnet, it's difficult to make it a piece of steel again. You to lose magnetism in here. The property here is it's easy to magnetize and demagnetize. Because of these properties, it's very obvious that you use this to make permanent magnets. Right? You don't want magnets to lose their magnetism. Because of this property here, you use this to make electromagnets. Because electromagnets, you want as soon as I turn on the current, it should become immediately a magnet. As soon as I turn it off, it should lose that. It should be demagnetized. And that is why you use soft iron. Is that clear, Arvind Thakur and everybody here? And we'll actually see quantitatively also. Like we'll draw the graph and see all these properties. Yeah, but then qualitatively first, if you get a big picture, it really helps you understand what's in detail there. So now we are going to summarize what we did via these slides. And these slides are really useful. So pay extra attention here also. So toroid, we studied magnetic induction without the core and then with the core. Core was that soft iron thingy that we introduced there. Now, without the core, we had mu naught Ni, and Ni we called it that as H. And this is what you got. Actually, I will let you study this. Anybody has a question can ask me. Take your time, try to understand this. Clear, Arvind, are you clear with whatever is written here? Everybody is clear, Sai Kumar, everybody? Linus Joy is clear, okay, Arvind is clear. Okay, Sai Kumar, Abhiraj is clear, okay. Now this is the next level that we went to. So then we said, okay, 1 plus xi m. You really have to have these on your fingertips. You should not be thinking that 1 plus Im is mu r and so forth. Okay, so let's move further here. Numericals. Okay, numericals on solenoid and toroid. That's the next section here. Formula list for quick reference there. We already have covered this mu naught small n or the lowercase n times the current. For a toroid, it would be n divided by 2 pi r because that's the length of the toroid, right? Given the radius. Now flux is B times A that we have studied many times. Flux is defined as a amount of field going through a given area. So flux was E times A in the electric world. It's B times A in the magnetic world. Take your time. Take your time and try to do this. Yeah, you can answer me in the chat box here once you have the answers. Nobody is able to do it so far. Okay, sure. Abhiraj needs more time, and I think everybody needs more time. So take it. Okay, thank you, Atri, for answering that. Thank you. Yeah, your answer is right, Atri. Yeah. Okay, thank you everybody for answering this. Let's do this together for students who did not get it. So a solenoid has this much of turn. What is the magnetic induction produced, right? So magnetic induction is mu naught n I, right? That's it. So then you say 4 pi into 10 to the power minus 7 multiplied by number of turns is 1000 divided by 20 centimeter doesn't look good. So 0.2. multiplied by the current 2. That's all. Right, so 4 pi times 10 to the power minus 7, and this will become zero point 0.1 here, so times 10 to the power 4. And as Atri was saying, and many others have said, 10 to the power minus 3, this is your answer. Right? And then students have given me the flux also. So you take this 4 pi into 10 to the power minus 3, and you multiply by area, which is pi d square by 4, or 2 square radius square, right, times 0.02 whole square. That is your flux. Anybody who did not understand, please ask me. No hesitations, please. Anybody who is not clear, if you have not understood, tell me, please. Here is a printed version for that. Okay, yeah, Aryan, yeah, Cengage is a very good quality book there. So yeah, in the background, Aryan is focusing on the background there. There is a series of Cengage books. Yeah, it's really very one of the good series. But if you're reading other books, do not switch to Cengage at this point. Any good quality book is good, right? So don't follow what others are doing, please. If you have been reading other books, just focus on that. Yeah, so Cengage, and then Irodov is another classic book, right? Resnick Halliday and H.C. Verma, no words about it. So all these are good books. Just pick one book and stick to that. So I'm just showing you the printed versions in case you need the printouts. And actually, you can leave the answers in the board exams. You can leave here, but when you have to give the choices, you're given choices. That's when you really calculate the values. Yeah, please try this question now. Oh, Weber, Weber. Yeah, let's focus on this question now. Okay, thank you, Arun Malik, for answering that. I will show you the solution here. That is it, right? So you just do same thing as we did earlier. Or if you want, let's do it here. So mu naught, right? Mu naught Ni. This is the magnetic field, but then you're not given N, you're given the total number of turns. So you can divide this by 2 pi r multiplied by I, right? So mu naught is 4 pi times 10 to the power minus 7 times n. N is 5000 divided by 2 pi times r, 0.25 times the current, 15 amperes, right? And then you do the calculation there. So remember, for toroid, you have to calculate 2 pi r as the length of the toroid because it's circular. Okay. Any doubts so far? Any doubts? Any questions? Any confusions? So again, a list of formulae just for ready reference. The more number of times you see them, the more you'll get comfortable with them. So magnetization, if you remember, we said is the magnetic moment produced per unit volume. Anybody who does not understand this part, magnetization is the amount of magnetic moment or the magnetic dipole moment per unit volume of the material, right? That's magnetization. So in this formula, we have already covered 3-4 times today. And then this one was something new that we studied, but it should be clear. So this is when there is vacuum, and this is mu r thingy, 1 plus xi. Okay. Take your time, try to do this. And I'm expecting right results here. I'll do all the steps here. Don't worry. I will do all the steps. Um, Anybody? Nobody was able to do this, is it? This is easy question. Honestly, this is easy question. I will write down the formulas that you would use here. B is equal to mu naught. Um, okay, somebody got it. Sai Kumar, your answer is perfectly right. Thank you so much. Yeah, that's really good. Ni, right? That's B naught when there is vacuum in there. Atri Patel, thanks for answering. Answer is not right actually, but thanks for trying that. Try again, Atri. That's what I'm saying. So that can also be written as mu naught 1 plus xi, right? I don't know mu r, then I can use 1 plus xi and I. So this is what you had initially, and this is what you have finally. You find final minus initial, divide by initial, multiplied by 100. That's all you do. Perfect, Arvind Thakur. That's absolutely right. Yes. Atri, try that again. You will be able to do. Shreya Bhatt, what happened? You have to participate. Rukaiya, what happened? Rhythm, Ninad, Monisha, M. Ashik, Abhinaya. Abhinaya has been talking. Yeah, that's good. Abhinaya, you have been speaking in the class. Linus Joy, you participated a little. Lakshmi, you also did. Yes, I saw that. Aryan is, yeah, Abhiraj, Atriya, fine, fine. Ganit, you have not spoken anything in the class. And Grishma, you should also participate a little more. Grishma, you're right. As soon as I said you participate more, you give the right answer. So what was stopping you earlier? Hesitation or what? Okay, that's fine. Grishma, good job there. Atri Patel, now you're getting the right answer. See? Good job, Atri. Anybody else? Trisha, give me the answer, please. Abhinaya, what is the answer? Okay, so I think we will do this together after the poll here. Let's see how much correct response I get. Uh, no, I don't have this. I don't have the poll for this. I don't have poll. So let's do it together. So the percentage change in anything, it's not about here, it's anything, is equal to the final value minus the initial value divided by the initial value multiplied by 100. That's how you find the percentage, right? So here the final value is mu naught, and I actually try to plug in the value at the very end. Why plug them now? You can simplify things and then plug in the values. That actually helps you a lot. Because look at this, you can take mu naught ni common here. So you get mu naught ni common. In there you get 1 plus xi minus 1 over mu naught ni. Don't plug in the values. Save your time, please. And then look how this all gets cancelled out. And 1 minus 1 is 0. So xi multiplied by 100 is your answer, which is equal to 6.8 times 10 to the power minus 3 percentage. That's your final answer. Anybody who did not understand, please tell me. If you've not understood, tell me, please. Okay, I'm going to move on because nobody is responding. This is the printed version here. Please tell me if you have not understood any part of this. I will explain you. Yatri, I don't know why you were not getting right before, but then you got it actually later on. So now let's see, this is the next page. 6.8 times 10 to the power minus 3. That's your answer.